Hello, in this video we're going to go over hydrocarbons and how to classify them. So again, hydrocarbons contain only carbon and hydrogen. Now, a hydrocarbon that contains only single bonds is considered a saturated hydrocarbon or alkane. And part of the reason we use the word saturated is to indicate that the maximum number of hydrogens are present. Unsaturated hydrocarbons, however, are called alkenes, alkynes, or aromatics. And they contain double bonds, triple bonds, or ring systems with alternating double bonds. So unsaturated hydrocarbons have less hydrogens than alkanes. So for example, if we look down below at our chart, we have all of our different hydrocarbons: alkanes, alkenes, alkynes, and aromatics. Alkanes, again, have the maximum number of hydrogens that a molecule can have. So we could imagine that all of these bonds here go to different hydrogen atoms. Alkenes, however, have two fewer hydrogens because of that double bond. So our alkane was C2H6. Our alkene is C2H4. So there's two less hydrogens there. So alkenes are considered unsaturated. Alkynes have even less hydrogen atoms. So this would be C2H2. So every time we add another bond between carbon atoms, we're losing two hydrogen atoms in the process. And then aromatics are a bit different. They're kind of in their own category, but because we have these double bonds in the ring, we know that there are two fewer hydrogens than the maximum number. So those are also considered unsaturated. So alkanes, our simplest hydrocarbon, can be represented by the general formula CnH2n plus 2. So the simplest alkane is methane, CH4, which is the primary compound found in natural gas. Now, if we use our formula up above, again, we only have one carbon in methane. So then to count the hydrogens, we're going to plug 1 in for N. So this would be 2 times 1 plus 2. So that would give us CH4. 2 plus 2 is 4. Ethane, C2H6, is a minor component of natural gas. Again, if we use our formula from up above, we have 2 carbons. So to count the number of hydrogens for an alkane, we would plug that in for N. So we've got 2 times 2, which is 4, plus 2 is 6. So that gives us C2H6. Propane has 3 carbons, so C3H8, and that is used as a fuel for heating homes and cooking. So again, if we use our formula, we have 3 carbons. So we would plug 3 in to our equation. That gives us C3H, let's see, 2 times 3 is 6, plus 2 is 8. Perfect. Okay, so if you're ever in doubt about how many hydrogens an alkane has, just figure out how many carbon atoms there are, and you can easily calculate the number of hydrogens. So down below, we have a figure of ethane, C2H6. So we've got the ball and stick model, and then the space filling model as well. Now, more complex alkanes can be straight chained or branched, as we've seen before. So as we start adding more carbon atoms on, so once we get to 4 carbons or more, now we have the opportunity to create these branches or isomers of our different alkanes. One other thing to keep in mind with alkanes is everything has a single bond, right? So all of the carbons have a single bond between them, and that means that there's free rotation around those single bonds. What we'll see later on is double bonds and triple bonds do not have free rotation. Only alkanes with all single bonds have free rotation. So for instance, if we're looking at butane, which is this 4-carbon chain, we could position it where everything is in kind of a zigzag pattern, or we could rotate that last carbon up, and now we have kind of a, let's see, a boat-looking conformation. So these different arrangements of atoms in space achieved by rotation about single bonds are called conformations. So just remember that you can freely rotate these atoms. All right, so now let's do a quick check of our knowledge here. Which of the following pairs below represent structural isomers, and which are simply the same compound? Also, which of the following are normal alkanes and which are branched alkanes? So I would like you to try this on your own first, so you can pause the video, try it on your own, and then when you think you have the answer, you can unpause and we'll go over them together. Okay, so I'm actually going to start by figuring out which of the following are normal alkanes and which ones are branched alkanes. Okay, so the way to kind of figure out if you have a normal alkane where everything's in a straight chain or a branched alkane is to try to draw a line without breaking off. So as you can see with this first one, initially it kind of looked like a branched alkane, right? But I was able to draw a line through all of the carbons without having to stop and move my pen. So that would be a normal alkane. Let's look at the one next to that on the right. So let's see if I can draw a line through all of the carbons. Yep, so that is a normal alkane. And now let's move to the bottom left. Oh, now there's a fork in the road. I could either go up or to the right. So I'm going to keep going to the right, but that means that we do have a branch that I couldn't quite cover. So this would be a branched alkane. All right, and let's do the same with the last one. Okay, so I was able to draw a line through 4 of the carbons, but I couldn't draw a line through that last carbon, so this is also a branched alkane. Now, you might be able to tell whether something's normal or branched just by looking at it. That's totally fine, but if you're not as familiar with this, then I recommend trying to draw a line through all of the carbons. And if you can, without coming, to a fork in the road, then you know it's a normal alkane. But if you do have a fork in the road and you have to make a decision, then you know it's a branched alkane. All right, so now let's figure out if any of these are structural isomers or if they're the same. So looking at the 2 on the top, they're both normal alkanes. They both have 5 carbons and the same number of hydrogens. So while they do have different conformations, the one on the right has a zigzag pattern, the one on the left doesn't. That doesn't really matter. They're still the same molecule. So these would be the same. They just have different conformations. So there was some rotation going on there. But then looking at the top left and the bottom left molecules, are those the same or are they structural isomers? They are different, right? One's a normal alkane, one's a branched alkane. They do have the same number of carbons, same number of hydrogens, but because we have this branch here on the bottom alkane, that's what makes these two structural isomers. Their atoms are in a different arrangement. All right, and then let's look at the two bottom structures. Are those the same? Yes, they are the same. So notice that we were able to draw a line through 4 carbons on the first one, and we were able to do the same on the second one. That was just in a slightly different conformation where there was rotation around one of the bonds. But they have the same branch, which is the CH3 group. So these are the same. And now let's compare the two structures on the right. Are those the same or are they structural isomers? Structural isomers, right? We could conclude that just looking at the last comparison. All right. And then there are some descriptions here. And another way to figure out if you have a branched molecule, there will be at least one carbon atom bonded to 3 or more other carbon atoms. So that's another way to figure out if you have a branched alkane. A normal molecule will not have any carbon atoms bonded to more than 2 other carbon atoms. All right, and then the top molecules and the bottom molecules are structural isomers of each other. The formula for both is C5H12, but the top molecules are normal while the bottom molecules are branched. All right, so we'll stop there for this video. In the next one, we're going to go over how to name alkanes. So I will see you then.